Okay, so let's start our lecture. And this is a common presentation with Professor Rao Mikkilineni. And this is about symbiotic computing. So we start with traditional forms of computations. And we know that there are different types and forms of computations. According to the forms of data process, two pure forms of conventional computations are studied: symbolic computation and sub-symbolic computation. Computers and the most popular models of computers and computations, such as Turing machines, they work with symbolic computation. They perform symbolic computation. However, such models as neural networks perform sub-symbolic computation. But what's necessary to mention that, as for now, all new artificial neural networks are simulated on conventional computers, which actually perform symbolic computation. So it's some illusion that contemporary artificial neural networks perform sub-symbolic computation. So what is symbolic computation? Symbolic computation is performed with data having the form of explicit symbolic systems, such as systems of numbers, icons, or letters. And the computing system operates with individual symbols. Here, symbols are defined as linguistic objects and not in a more general philosophical sense. Sub-symbolic computation is performed as transformations of data described by non-linguistic objects, such as specific signs, signals, or geometric relationships. Note that sub-symbolic computation can be modeled by symbolic computations. As I already said, that now all artificial neural networks are actually simulated by conventional computers. In both cases, that is symbolic and sub-symbolic, the transformed entities are represented by the states of the computation system and by the states of its elements. Thus, to portray and study computation systems and their functioning, researchers use various mathematical models of computations, such as recursive functions or Turing machine, which work with separate symbols. Sub-symbolic intuitive computation means that the machine or computation system uses elementary operations with concealed semantics. Examples of such machines are neural networks and cellular automata. Sub-symbolic intuitive computation allows elimination of explicit algorithms, programs, and using instead optimization processes which improve functioning of the machine by upgrading implicit algorithms and programs of the machine. It's necessary to remark here that the majority of computer scientists think that when sub-symbolic computations are performed, they don't have algorithms that control sub-symbolic computations. However, this is only an illusion because actually there are algorithms, for example, for functioning of neural networks. Only these are implicit algorithms that are uh, that are determined by different functional parameters of artificial neurons. Some symbolic intuitive computation is realized by the neural ensembles in the brain. Researchers of cognition conjecture that the object formation can function as a transition from a stream of massively parallel subsymbolic microfunctional events to symbol-tied serial processing through subsymbolic integration. Subsymbolic intuitive computation is a model of functioning of the emotional and affective systems of the human brain. Symbolic rational computation means that the machine computation system uses elementary operations with elementary objects having individual semantics. Examples are Turing machines, inductive Turing machines, and vector machines. Symbolic rational computation is a model of functioning of the left hemisphere of the human brain. The advantage of the symbolic rational computation is the explicit form of the algorithms and programs that control and direct the functioning of the machine. At the same time, the general theory of structures and brain neurophysiology point to one more pure type of computation. Indeed, if there is a symbolic computation, then it must be supersymbolic computation, in which superstructures are transformed. Supersymbolic transcendent computation is a model of functioning of the right hemisphere of the brain. Processing of images by operation with holistic shapes is an example of supersymbolic computation. The advantage of the supersymbolic transcendent computation is its ability to operate and transform big formal and informal systems of data and knowledge. It's possible to suggest that the problem of big data can be solved using supersymbolic computation, which work not with separate item of data, but with big structures of input data. Implementation of supersymbolic computation is the way to the solution also of information overflow. Symbolic structures are composed from symbols in a simple way. That is, these structures have low structural complexity. Symbols, words, text as linear compositions of words, and sets are symbolic structures. Symbolic superstructures are composed from symbols and symbolic structures. Intricate hypertext, multi-component images, structures of higher order are symbolic superstructures. This gives us three pure types of computation: subsymbolic computation, symbolic computation, and supersymbolic computation. which was not studied before. Combination of few types gives mixed types of information processing. The first step in this direction gives us hybrid computation, which comprises both symbolic and sub-symbolic computations, being a two-fold type of computation, which was considered in the paper of my paper with Gordana Dodik-Kronkovic, published in 2015. Hybrid computation allows combining advantages of both symbolic and sub-symbolic computations. Conventional models of computation perform either symbolic computations, for example, finite automata Turing machines, inductive Turing machines, or random access machines, and sub-symbolic computations, for example, neural networks or cellular automata. New models such as neural Turing machines or structural machines with symbolic and sub-symbolic processors carry out hybrid computation. A neural Turing machine is a new model of automata that combines a recurrent neural network with a network controller connected to external memory resources. As a result, a neural Turing machine combines sub-symbolic computation of neural networks with symbolic computation of Turing machines. Super-symbolic or intuitive computation adds one more dimension to the general schema, synthesizing super-symbolic computation with symbolic rational computation and sub-symbolic intuitive computation in one model. And in such a way, we come to symbiotic computation. So symbiotic computation combines symbolic, sub-symbolic, and super-symbolic types of computation in the same computational process. Structural machines with flexible types of processors can accomplish symbiotic computation. Symbiotic computation allows combining advantages of all three pure types of computation, representing the entire type of computations. As a result, we have three pure types of computation: sub-symbolic, symbolic, and super-symbolic computation. Three two-fold types of computation: hybrid computation combines symbolic and sub-symbolic computations. Blended computation combines sub-symbolic and super-symbolic computations. Fused computation combines symbolic and super-symbolic computations. And the entire type of computations that is called symbiotic computation combines all three pure types of computation. Now we have mathematical apparatus that allows us to formalize our previous ideas. And I'll show you naturally not the whole mathematical apparatus that is mostly represented by the general theory of structures and its logic, but only some lower levels of this theory, lower levels of structure. So we have on the first level, first order structure. And a first order structure is a triad of the following form. A bold is equal to A capital, R small, and R capital bold, and very capital. And in this expression, we have the set A, which is called the substance of the structure, A bold, and it consists of elements which are called structure elements of the structure A. The set R bold and very capital is called the arrangement of the structure A and consists of relations between elements from the substance A of the structure A bold. And for the first order structure, R bold capital consists only relations of the first order, which are called structural relations of this structure. And the middle part is the R is the incidence relation, which connects groups of elements from the structure substance A with the names of relations from R. Here are some examples. Order on numbers, 1 is less than 2, 2 is less than 3, 3 is less than 4, 4 is less than 5, is a first order structure. A string A and B, C, D, E is a first order structure. Relations are relation between consequent symbols. Word, for example, 7, is also a first order structure. Another example is a graph, where elements from the substance are nodes or vertices of the graph, and relations are edges of this graph. Then one more example is a labeled graph. Can you see the different colors of the edges in the picture of the labeled graph?
Yes, so one is bolder than the other one is lighter.
So my computer does not give the whole picture because actually
everything is green.
These edges are have different colors, and colors represent labels on these edges. So we have connection of edges also to elements that are called labels, and in this case, labels are colors. Maybe when my co-author, Rao Mikkilineni, will continue this talk, he will be able to show on his screen better image of the labeled graph. And now we'll continue with this. Then on the next level, we have second-order structures. And the second-order structure is also a triad of a similar form, A bold equal to A, capital R and R bold and very capital. And A is also the substance that contains elements of the structure A, but the set R consists of three groups of relations. So R is equal to R1, union with R2 and union with R3. R1 is a set of relations between elements from the set A. So this is the same as in the previous case of the structure of the first order. Now R2, this is R2, is a set of relations in the set R1. So it's relations between relations. And R3 is a set of relations between elements from A and relations from R1. And the relations from R2 and R3 are called relations of the second order. So the difference between structures of the first order and structures of the second order is that structures of the first order contain only elements, only relations of the first order, and structures of the second order contain relations both of the first and second order. And examples of relations of the second order are here. For example, the strict order on numbers is a suborder of the non-strict order on numbers. A suborder is a relation of the second order. Addition and subtractions are ternary relations. Subtraction is inverse to addition, so this inversion is a relation of the second order. Okay, here are also some other examples. For example, taking relations between people, then if you say that relations between A and B are better than the relations between A and D, this better defines a relation of the second order because it's relation between relations. And now we have also techniques and theory that supports our types of computation, that such automata that can perform symbiotic computations, and they are called structural machines. I will not go into the theory of structural machines. It's a big theory. It's not as big as the theory of Turing machines, but it has many theorems and many results and many constructions. So let's look very briefly what are structural machines. So a structural machine works with structures of a given type and has three components. The control device regulates the state of the machine M. The processor P performs transformation of the process structures, and its actions depend on the state of the machine M and the state of the process structure. And the third component of a structural machine is the functional space, which consists of three components: input space, output space, and processing space. For those who know what a Turing machine is, the functional space is a far-reaching generalization of the concept of a Turing machine tape. And it represents in some sense a memory, but in some sense an extended memory. And computation of a structural machine determines the trajectory of computation, which is a tree in a general case, and a sequence when computation is deterministic. There are three forms of functional spaces, but I will not go into these details. There are also three basic types of control devices. Due to the restrictions on time of our lecture, I will not go into this part of the structural machine, but what's important is that there are three basic types of processors. A localized processor is a single abstract device, which is a processor unit or a unit processor. But there are more powerful processors, and a distributed processor, or which is also called a total processor, consists of a system of unit processors or processor units. And a spread processor, which is called also an entire processor, consists of a system of clusters of unit processors or processor units. So one processor actually can comprise actually any number of unit processors, and it allows structural machines to transform very complicated data structures, and as well rather complicated knowledge structures. And here are some examples of distributed processors. For example, processing devices in evolutionary automata, such that evolutionary finite automata, evolutionary Turing machines, or evolutionary inductive machines, are distributed processors. Cellular automata give also an example of structural machines with potentially infinite distributed processors, in which unit processors are identical finite automata. It is possible to build structural machines that work not only with discrete, but also with continuous data, because structures can be continuous and there are no restrictions on relations in process structures. And so structural machines comprise all kinds of artificial neural networks, Shannon's differential analyzer, finite dimensional and general machines of Bloom, Schubert, Smale, and type 2 Turing machines of Weinrauch. And now we come to the second part of our lecture, which will be delivered by Rao. So Rao, I stop sharing my screen. Please take from this point our lecture.
Perfect. Thank you very much, Mark. I'm bringing up my screen, and we'll go from there. Share. Okay. Can you see my screen?
No, oh, now yes.
Okay, so let me put it in the slideshow mode. And from current slide. Okay, so I'm going to now talk about essentially how we can take these structural machines and structure the physics of, mathematics of structures into actually implementations of computing engines that will combine deep learning and also the symbolic computing or the algorithmic computing. So just as the Turing machine was the origin for John von Neumann's stored program control, we will be able to now use the structural machines to design and implement actual computing processes that actually give us the integrated computing of both the artificial intelligence and also the subsymbolic and symbolic computing. So here is actually a very interesting announcement by the Oak Ridge National Laboratory. They are trying to come up with some new class of computers that really go beyond conventional computing and current neural network. For example, this face here, is it a vase or there are two faces, right? And so the conventional analysis will give you either a vase or the faces. But the new probabilistic computer that they are proposing actually will give you 50% of the time the vase and 50% of the time the faces. And so the result will show that it could be either, right? And so essentially, here is basically with the brain-inspired computing, and they talk about, I have a link here, and this will be posted in our session screens, so you can take a look. But the important thing I want to point out here is conventional computers can look at the optical illusion, but in order to really address this, we need a different kind of computing. And that is essentially comes from the structural machines and the theory of structures based on general theory of information that Professor Burgin has talked about. So information has always been considered as a fundamental constituent of the universe on par with matter and energy, and the missing link in the explanation of all the phenomena of the world. And there are basically between these, other scientific streams consider information as something that pertains only to human beings. But I think the current understanding is essentially the existential triad and the information structures of the general theory of structures, general theory of information that Mark Burgin has proposed is that the whole world consists of either a physical world or a mental world. And both of these are represented in in the structures. This is where the theory of structures comes in. So the theory of structures, the physical world is in physical structures, whereas the mental world is in mental structures. These are things that your mind conceives and so on and so forth. And only certain types of physical structures can have mental structures. So for example, living organisms have mental structures. And these mental structures also can have their own created structures, but they both can be represented by the theory of structures. And essentially you can bring in the structures, physical structures and mental structures, and you can represent them in a common form using these structures. And that's essentially what we are going to do. And information is related to knowledge and data as energy is related to matter. And this is where the biology and the computer science essentially combine to give us new models of computation. So I'm going to talk about essentially, information expresses the fact that a system is in a certain configuration that is correlated to the configuration of another system, and any physical system may contain information from another physical system. So information is really not a physical structure, but it is contained by physical structures as carriers, and it is exchanged by carriers from one entity to the other, and also it is processed by physical structures. So in order to essentially get information, you need a physical structure to process them. So general theory of information tells us that information is represented, processed, and communicated using physical structures. The physical universe as we know it is made up of structures that deal with matter and energy. Information is related to knowledge as energy is related to matter. This is the general theory of information. And so essentially what we have here is the information comes in, and that essentially is an observation, or it is a mentally conceived information, but that has to be converted into knowledge. And that knowledge is really where we will use the theory of structures to represent this knowledge in terms of the graphs, in terms of entities, in terms of relations, in terms of relationships between relationships, and in terms of behaviors. So combining this into the model where you can actually represent not only the entities and the relationships that we do with conventional data structures, we also include the behaviors and how the structures evolve as graphs. And that is really the difference between the data structures and the knowledge structures. So we are going to now represent all our knowledge take the information, convert it into entities, relationships, and behaviors, which are the knowledge structures. And then the cognitive apparatuses, like, for example, in the brain, it is your neuron and your gene. In the case of computing structures, it will be a symbolic computing structure or a subsymbolic computing structure. We use them for essentially evolving the state of the knowledge structure from state 1 to state 2, and identifying the information, and that essentially gives us the insights and so on. So here is your the science of information processing structures. And actually this is based on the named sets and also the structures, the theory of structures. So as you can see here, the relationships and the behaviors, entity 1 and entity 2, this is really the data structure for knowledge structure. So the knowledge structure is an evolution from the data structure, where the relationships and the entities and the behaviors are all captured. And as Mark pointed out, there is a control device, and there is a processor, and there is input space and the output space. And the input space now consists of the knowledge structure instead of the data structure. And you have output space also is output of the processing on this knowledge structure. And basically, Mark also has defined what these knowledge structures are. What is a schema for a knowledge structure, just like a schema for a database, and what are the operations on the knowledge structure, just like an operations on the database. But the difference is, whereas the database uses the data structures, the operations on knowledge structure uses knowledge structures with the operations on behaviors, entities, and relationships. And this is where the major difference comes. And we are going to use this actually to implement the super symbolic computing architecture and actually apply it to build some software that is autopoietic and also cognitive. So here is a knowledge structure example. So for example, I have here object 1, which has a few attributes, attribute 1, 2, 3, and 4, and I have an object 2 with another set of attributes, and object 3 and an object 4, which is isolated and it is not connected to the other objects. However, attribute 1 is connected to attribute 4. What that means is the relationship of attribute 1 to attribute 4 is essentially whenever something changes in the attribute 1, it will cause an attribute 4 change. So these CRUD operations on attribute 1 immediately execute a communication to attribute 4, and the attribute 4 has now behaviors that this communication will fire up. So this is essentially like the neurons getting fired when you get some new signal. And so essentially this allows us to propagate communication signals and then use those signals to actually propagate the behaviors. So attribute 1 here may affect attribute 4, and that may affect attribute 2 in object 3, and so on and so forth. So this allows us to now essentially do a structural machine modeling application with behaviors. So you have 3 layers. And so here is your applications, and the bottom layer, knowledge structure modeling the application behavior. And so we have knowledge structures here. We are modeling the behaviors of these, because these are all just entities and relationships and behaviors. So we model those, and then we use operations on these models as a graph. So essentially these models here, the knowledge structures, the operations of them are just essentially reconstituting the graph, or changing the nodes, or adding the nodes, or adding the links, and so on. And the behavior itself is independent of the domain, because that is hidden in over here. So the knowledge structures modeling the application hides all of the details of the application. However, it will provide a way for the information to be shared, and the shared information to cause workflow changes across the system. And this is the major breakthrough in terms of how we go from Turing machines to structural machines. We go from data structures to the knowledge structures, and deep learning to deep reasoning. That's what I'm going to show you, how we do it and how we implement it. And we have an example of implementation we are currently working on. So this is a structural machines also enables basically super symbolic computing, and the cognitive behaviors are essentially related to the super symbolic computing behavior, and they cannot be essentially either done with the brain model alone, or the body model alone, or it is a symbolic computing alone, or super symbolic computing alone. So the Burgin-Mikkilineni thesis we proposed is that the autopoietic and cognitive behavior, if you want to actually model in a digital system, you need to be able to essentially use the knowledge structures and the structural machines. And the structural machine provides you with the mechanism to infuse autopoiesis and also cognition. And that's basically the idea. And here is your super symbolic computing. And I'm comparing this with how the actual brain works. So brain also has your symbolic computing at this level, because all your symbols are A, T, C, G, and that is the DNA. And then it is grouped into chromosomes, and then all of this stuff is also, there is the sub-symbolic computing neural network, and the 5 senses essentially go through this cortical columns, and then this data, 5 senses signals, are converted into local knowledge structures, and these local knowledge structures are converted into, basically the neural maps are the knowledge structures, and then you have your neocortex processing them, and so on and so forth. So if you look at this, sense, observe, and manage, this is the data that is coming in, information that is coming in, and then that goes into remember and memorize, and that goes into essentially either mimic and learn, or abstract and model, and reason and predict. And then you basically, based on the predictions, you take action. This is where the free will comes in, and you make a decision to act on your recommendation or not. So this is the mind-brain-body model. And essentially it shows that you have symbolic computing, you have sub-symbolic computing, and you need a super symbolic computing in order to do collect the information from five senses and create a elevated cognition. These five senses are also cognitive. And so you have to have a higher level computation that essentially does that. So we are going to take the same model and apply the data structures to knowledge structures. And we will take the structural machines instead of Turing machines, but we can actually implement the structural machines using the Turing machine as a substrate, right? So here is your physical world, and you have a lot of knowledge from here and information that will be converted into knowledge, and you have a mental world, mathematics, etc. And all of this is also going to get converted into, this information converted into models and knowledge. And in the digital world, we use this algorithmic programming as a digital gene, which is essentially an algorithmic program. And here is your neural network, and this is your digital neuron. And so we use these two as apparatuses, basically cognitive apparatus, convert information into knowledge structures and process the knowledge structures. Now, essentially, all of this is provides a sub-symbolic computing, and this is symbolic computing. Now, what we want to do is, how do we take these knowledge structures and implement a higher level super symbolic architecture so that we can essentially provide autopoietic and cognitive behaviors into our IT architectures. So here is a application that we are trying to essentially take multiple clouds and multiple infrastructure and multiple platform as a service like databases. So here is your CPU and memory comes from your IaaS, and your databases, application servers, and all the middleware and web servers, they are all come from here. However, this is all your senses and five senses, and essentially this is where you get your fuel for your computation. And here is your application, which is essentially now has a concept of its own self and its own autopoietic behaviors and cognitive behaviors. And these essentially modulate how you are going to use your application, which resources you are going to use, how you are going to manage the resources, and so on. And it turns out by using this model and by implementing this super symbolic computing over here, which is represented in blue, we can essentially provide location transparency for any application. It becomes completely path agnostic. For example, here, I can have a MySQL server, and this application can be using locally MySQL server, but it can communicate with another Oracle server over here. And so it is heterogeneous and independent of infrastructure or the middleware. And this is a major advantage because it reduces complexity and it provides no vendor lock-in and so on and so forth. So that is really where the application of this super symbolic computing, which is essentially taking your both symbolic and sub-symbolic architectures and combining them to create a new autopoietic and cognitive behavior for the application. So the application essentially is like a digital genome. We can specify the whole life of this application, how it can replicate itself in any computer, any cloud, and essentially how it can essentially use the local services available in order to provide the CPU and the memory and set up the right database, and then load the application workload and monitor the application workload. And if there is a failure here, move the traffic to another application or bring up another application in another cloud and do this, right? So essentially, like your cellular organisms, basically the behavior is autopoietic, so it can create its own replica anywhere and connect it with it. And so it creates a distributed self. So because here is a distributed self for how I can use my local resources and how I can create my local middleware, etc. So I think basically that's what I wanted to point out, that the structural machines and the knowledge structures, we can actually use them in real life, and we can actually build systems that are useful. And here is the model where you have on the left-hand side how the brain works and how the genome works, and here is the digital genome and the autopoietic machines work on this side, and how both sides you have 5 senses, sensors and actuators, and they cognitive modeling, and this gives a basic knowledge structure that can be across multiple senses. So it is independent of how the data is acquired, but it is represented as a knowledge structure, which is, by the way, a graph. So I will stop here, and we'll have about probably 10 minutes questions, because there is a lot of stuff here. And this is all, by the way, new. And we are going from classical computer science to the science of information processing structures. So it will take a while for people to digest and appreciate and also apply. So I'm very open to questions now. And also Mark.
Well, do we have any questions? I hope we do.
Wow, it must be crystal clear.
Well, it is complex.
Obviously.
And
yes,
novel.
Obviously. Right.
Okay,
Obviously.
sometimes too much information is even worse than too little information.
Okay, then I will ask the question that I'm interested in. I don't know that because not everybody knows of this cognitive architecture called DABUS, D-A-B-U-S, by Steven Thaler. He was definitely working on just regular discovery engines, based on one kind of improved randomizer and one selector that wasn't so relevant here. But now I think DABUS is working mostly on in transformation of images and some other symbolic or sub-symbolic information, probably the former. So if you had any comments,
yes.
and he will have his presentation on the patent for DABUS, because it's so autonomous that actually he thinks it deserves a patent instead of his programmer like himself, like Thaler. So that would be one of our keynote speakers on the 17th.
Yeah, actually, most of the AI people that are coming up with the similar kind of controllers and controller architecture, they are coming up from bottom up. Whereas the structural machines gives you a top down, just like Turing machine theory by Alan Turing, essentially sort of set the stage for how John von Neumann could use a stored program controller and so on and so forth, right? So it's a top-down architecture where you define cognitive behaviors and all the autopoietic behaviors, and you can then implement. So for example, this application workload here could be your image processing application over here, and it could be your voice application over processing over here. And here is a sensors and the actuators that will, based on the result, can take some action on real life, programs and real life, switch on the light or whatever, right? And so essentially this architecture allows for you to now run your DAOs over here and get to all the insights from whatever you get from there. And you can run DAOs on images over here and some other application of audio on here. And you can use this information while the programs are running. That information is available in the cognitive layer. And this cognitive layer now can use this information while the programs are going on here, and modify the program over here. And this is a very important part, because changing the behavior of another application based on what is going on in another process while they are all running without disrupting the programs, either one, is a major advantage and also a major breakthrough in computers science, right? Because today you cannot do that, and that is why Mark has invented inductive Turing machines and so on and so forth, right? And so the structural machine gives you already the autopoiesis and the cognitive layer, and so you can program all the stuff on the from top down, and then you can implement your bottom up processes, whatever you like.
Great, thank you for this thorough explanation. And of course, some of them don't have to have actuators in, like robotic, but can just get, they would be cognitive architectures functioning. But I have one very simple question, because the term autopoietic is used, it's an old term that has different meanings. In AFN and ANN, you use it as a very technical term. Could you present this term a little bit more clearly? Because, 2 or 3 meanings come to my mind at the same time.
Yeah. So essentially, for example, autopoiesis, involves replication. So it can, for example, this digital genome here has the whole application, complete application knowledge over here. And this essentially can replicate itself here and activate only some portions of that gene. And so essentially, this allows you to replicate and also turn on and turn off only certain portions of the program, just like the genes do. And so auto scaling, auto failover, self-protection, all of those are now possible. Those are called autopoietic functions. So self-repair, self-protection, auto scaling, and migration, live migration without disturbing the transaction.
Thank you. It's time for other questions. I hope there are some. Questions, comments, maybe?
By the way, I have written a lot of explanations of all of this and why we need this in my blog post on tffpis.com, and so that is the website for Theoretical Foundations program, and tffpis.com. You will see a large number of references. Mark's books are quoted, and I have actually written many blog posts, and I'm going to continue to elaborate on this so that people can apply this very quickly into their own scientific endeavors.
If you could type this into the general chat for a moment, because
definitely
that would be very helpful, for people not to get misspelling or something.
Right.
Yes, I have one general question. If there are no other questions, how super symbolic computing is connected with maybe the work of Damasio, because it sounds like it would go in that direction, mind maps. I have a paper in Procedure Computer Science maybe 4 years ago called Strong Semantic Computing. The title sounds like something else, but it's exactly going in that direction by kind of putting in brackets or mostly syntactic computing, but that would be a different story. So my question is, am I still audible?
Yes.
Yes. Okay.
Yeah. You are audible. Yes. Actually, I have a presentation tonight at 10 o'clock in Markham, which is actually talking about digital consciousness and relating this work to essentially what Damasio and Stanislas Dehaene, they all have been talking about, what are the ingredients for cognition and consciousness. And so I'm identifying what those ingredients are and how to use those that knowledge to infuse cognition and autopoiesis so that we can build these systems in the computing. And so I'm going to talk about that. Actually, I have some videos from Damasio and also Stanislas Dehaene.
So that's good, but you said today at 10 p.m. in what session? And because it sounded like when do you have today?
Yes, tonight.
Tonight, but what session is it?
Markham, MORC. Yeah.
Okay,
It is in
thank you.
the invited talks in the mark.
And the time is UTC,
10,
yes?
10 p.m. in Los Angeles.
UTC, we are in the States here, so here this is, okay. So it is 10 p.m. UTC or?
No, not 10 p.m. UTC, 10 p.m. in Los Angeles.
Oh, 10 p.m.
In Los Angeles.
LA. Okay, all right. We have problems with those different times. Okay, so who would want to add final comment or anything? Professor Burgin?
Okay, I said everything that I wanted.
Very good.
But one last remark is that is only the tip of the iceberg of the general theory of structures. And it's also a big theory.